All right, let's talk about one of the most elegant and honestly, one of the most common shapes in our universe, the parabola. You've seen it everywhere. The perfect arc of a basketball shot, the curve of a satellite dish, even the cables on a suspension bridge. But what is it really? What's its mathematical DNA? Well, today, we're going to decode it.
So here's our game plan. We're going to start by seeing where this shape is literally born, by slicing a cone. Then, we'll uncover its one golden rule. After that, we'll break down its anatomy, part by part. Then we'll get into the algebra, the standard equations, and we'll wrap it all up with a master cheat sheet that puts everything in one place. Ready? Let's do it.
Okay, first things first. You gotta understand that a parabola isn't just some random U-shape that a mathematician dreamed up. Nope, it's a real, physical curve that you can create with a very specific action. Just look at this. Imagine you've got an ice cream cone, right? A perfect cone. Now, take a flat sheet, a plane, and slice through it. But here's the trick. You have to slice it at an angle that is exactly parallel to the slanted side of the cone. If you do that, the edge of the slice you create, that beautiful curve you see there, is a perfect parabola. That's its origin story. It's literally a slice of a cone.
So, we've got our shape from the cone. Let's take that curve, lay it flat on a 2D plane, and really look at it. Because now, we can define it not by how it's made, but by its single most important, most fundamental property, its golden rule.
And here it is. This is the big idea. A parabola is basically a club. And to get in, every single point has to follow one strict rule. Each point on that curve must be the exact same distance from a special point, called the focus, as it is from a special line called the directrix.
And this shows it perfectly. Pick any point on that curve. Let's call it P. Now measure the distance from P straight to that focus point, S. Then measure the shortest distance from P down to that directrix line, M. I guarantee you, those two distances will be exactly the same. SP always equals PM. That is the unbreakable law of every single parabola in the universe.
You know, this perfect one-to-one balance gives the parabola a unique mathematical fingerprint. It's a property called eccentricity, which is really just a fancy way of measuring how stretched out a conic section is. For a perfect circle, the eccentricity is 0. For a parabola, because those two distances are always equal, its eccentricity is always exactly 1. Not close to 1, it is 1.
Okay, so now that we know the golden rule, let's get familiar with the key players. Let's break down the anatomy of a parabola and give all the parts their proper names.
So every parabola is built on a basic frame. You've got the axis, which is its line of perfect symmetry. It slices the parabola right in half and runs straight through the focus. And then you have the vertex. That's the main point, the bottom of the U, where the curve makes its tightest turn and changes direction.
Now, the focal distance is pretty much what it sounds like. You pick any point on the curve, and it's simply the distance from that point back to the focus. And what's cool is that for a standard parabola, there's a neat little shortcut to find it. You just take the point's x-coordinate and add the value a, where a is the distance from the vertex to the focus. I know, it's a funny name, latus rectum, but it's super useful. It's the specific line segment that passes through the focus, is perpendicular to the axis, and has its endpoints on the parabola. Basically, it tells you how wide the parabola is at its most important point. And get this, its length is always exactly 4a, or 4 times that distance from the vertex to the focus. Always.
All right, we know the shape, we know the parts, we know the rule. Now it's time for the really cool part, translating all this beautiful geometry into the powerful language of algebra. Let's look at the equations.
So check this out. Anytime you see an equation with a y-squared term like y squared equals 4ax, you know instantly that you're dealing with a horizontal parabola. It opens sideways. And look at the power of a single plus or minus sign. If it's a positive 4ax, it opens to the right. If it's a negative 4ax, it just flips over and opens to the left. Simple as that. And you guessed it, the exact same logic applies here. If the x term is the one that's squared, you've got a vertical parabola, the kind that opens up or down. An equation like x squared equals 4ay opens up towards the positive y-axis, and x squared equals negative 4ay, it just flips and opens straight down. The variable that's squared tells you which way it's oriented. It's a beautiful, simple system.
Okay, I know that was a lot of info. Focus, directrix, latus rectum, all those equations. So let's pull it all together into one single, powerful cheat sheet that has everything you need at a glance.
Here it is. This table is your new best friend. You can see all 4 standard forms lined up. Notice the patterns. The eccentricity is always 1. The length of the latus rectum is always 4a. Those never change. The only things that shift are the locations. For horizontal parabolas, the focus is on the x-axis, at a, 0 or negative a, 0. For vertical ones, it's on the y-axis, at 0, a or 0, negative a. This table puts all those rules right in front of you.
So if you're going to walk away with just two things, make it these. First, the golden rule, a parabola's eccentricity is always 1. That's its identity. And second, the quick trick for spotting its orientation. Look at the equation. If the y is squared, it opens sideways. If the x is squared, it opens up or down. Nail those two things and you've got the core of it.
So we did it. We went from a simple slice of a cone all the way to its algebraic code. We've cracked the parabola. So now the real question is, armed with this knowledge, where are you going to see it next? Will it be in the gentle arc of a water fountain, the powerful curve of a radio telescope, or maybe the simple path of a ball you toss in the air? Once you know the code, you start seeing it everywhere.